Hello everybody, this is the first video clip for chapter 7, which is our last chapter for this course. Okay, uh, for this chapter we are going to talking about the Riemann integral. Okay, you have learned the Riemann integration during your math 2 already. However, you start with the so-called anti-derivative, okay, which is something that opposite to the derivative, okay, finding derivative, and then later on you are talking about the definite integral, right? The definite integral, which will be involving the Riemann sum, okay, and this Riemann sum will give you the application about the integration on the area under the curve, right? So for this chapter we are going to start from this one first, the Riemann, okay. However, we are not going to go over the so-called Riemann sum, but we are going to like talking about only one kind of Riemann sum, and then talking about the definite integral, okay, and also maybe a little bit about the area and go back to this antiderivative, okay. So this is the roughly speaking the plan, okay. So to define the Riemann integral, or to talk about the function that you can find a Riemann integration, okay, we are going to talk about the first section, which is called the Riemann integrability, okay. So let us talk about the definition first, okay. If you got your function f from the closed interval ab, which is bounded, okay. So for this chapter, the function that we're talking about is already bounded, all right. And then we are going to do a partition of this closed interval AB, okay. So by partition, it means that you are going to subdivide this interval from A to B into like n subinterval, okay. So as you may remember, this one, let's say this is A and B, this is your curve, okay. And then what you are going to do is to let this one as your x0, this one as your xn, okay. And you are going to subdivide this interval into smaller pieces, okay. So this one x1, x2, x3, etc, okay. And then for each k, okay, for each k from this one, I'm sorry, this is from 1 to n, okay, we are going to let your mk to be the infimum, okay, of all the function value f of x, okay, within this closed interval from xk minus 1 to xk. So if your k is 1, you are talking about the first interval, right, from x0 to x1, okay. This is like if your k is 1, you are going to find the infimum or of this function, okay, inside this closed interval. So for example, for this one, the infimum is right here, so you are going to choose it right there, okay. And sometime if the infimum is not the left end or the right end, you need to choose like that minimum, okay, or that infimum of the function instead, okay. Later on we are going to have the example, all right. And capital MK, of course it will be something in opposite, right, because previously we used the small mk as an infimum. The capital MK will be the supremum of the function value in that interval. For example, for look at this one, maybe the maximum, okay, or the supremum in this interval will be on this end, so we are going to choose that one instead, okay. And then we are going to define, I mean, for a particular partition P, okay, we are going to define the so-called lower sum. So the lower sum, we are going to collect all the infimum together, multiply with the length of each interval. So note that each interval may not have the same length. Okay, we didn't say that each interval need to be of the same length. Okay, it can be like in several kind of lengths. Okay, depends on what you like to choose. Okay, so this one is going to be your infimum of each subinterval multiplied by the length of that subinterval. So for example, it means that one of them, okay, each one of them before you do the summation, it will be the area of one strip over here, okay, over this closed interval, and then you are going to collect all the area of the strip together, okay, as you add them up from 1 to n, okay, from 1 to n. And of course, on the other hand, if you're talking about the upper sum, so the upper sum will collect all supremum of each of the interval, right? And we do the same thing, that we are going to multiply the supremum, okay, over that closed interval, and then with the length of each closed subinterval, so that we have each one of them before added, okay, it will be the area of a strip, okay, over that closed interval from xk minus 1 to xk, okay, and then later on you are going to sum all the area together, okay, to get your upper sum, okay. And after you have the lower sum and the upper sum, okay, for the lower sum, this will be a little bit what should I say, a little bit tricky, okay. For the lower sum, we are going to define the lower integral, okay. For the lower integral, we are going to find the supremum of all lower sum, okay. So please be careful. All right, the lower sum, firstly, at first we define from infimum of each function value on each subinterval. However, to define a lower integral, you need to find the supremum of all lower sum that you can find over all partition that you can think of, okay, on the closed interval AB, okay. And on the other hand, if you are going to define the upper sum, the upper integration, of course it will be from your upper sum, right? But it will be in the opposite way. You are going to find the infimum over all upper sum, okay, as you vary your partition P, okay, as you vary your partition P over this closed interval from A to B, okay. So this is the way we define the lower integral and the upper integral, okay, of the f from the lower sum and the upper sum, okay. So let's look at the picture for a moment, okay. For example, this is a curve, okay, this curve of a function here over the closed interval from A to B, and then we subdivide this interval into three pieces, okay. So right here is your x1, right there is your x2. So for this subinterval, okay, if you are going to find a lower sum, okay, you are going to find the infimum over this subinterval, which is right here, and then you are going to draw a horizontal or like this, okay, and then find the area of this strip, right? How about over this subinterval, which one is the infimum of this function? Okay, it happened to be on this side, so from this side you draw a horizontal line and then create a strip here and find the area of this strip as well, okay. And over the last interval, okay, the infimum happened to, the curve look like that, and the infimum is somewhere here. So from this one, you just draw a horizontal, okay, tangent to that point, and then this one will be the area of the strip over this subinterval, okay, the last subinterval. And as I told you, each of the interval may not have a different size, okay. So this one will be a picture for the lower sum of this partition, okay. So if we use the same partition, okay, please try to look at it as the same picture, but look at it in another angle, okay. This is the same curve as above, and then this one is your x1, this one is also your x2, okay, the same subinterval. However, this time we are going to find the upper sum, okay, the UPF, like that, for this partition P. Okay, over this interval you need to find which one is the supremum, and you can see that it's right here. So you draw a horizontal and then make it to be a strip over this closed interval, and you find the area of this strip. Over the second interval, you may see that here is your supremum of the function value. So you draw a tangent line to that supremum, and then here is a strip, okay, to get your area of this one. All right, and the last interval right there, the supremum is right here. So you draw a strip like that, okay, and find the area, and then you add these, I mean, three area together to get your upper sum of this function f for this partition, okay. And roughly speaking, as you may know before, if we do a finer, okay, partition, all right, for example, just like that, and we still keep the, let's say, a lower sum, okay, we still keep a lower sum over here on this interval. Here's the lowest, right? And on this interval, this one is still the lowest, okay. On this interval, this one's still okay, the lowest, but this one is the lowest sum, okay. You may see that the area under the curve that you haven't earned before, okay, you earn it as you do the finer partition, you see, for the lower sum. How about for the upper sum, okay? So for example, if you do a finer partition, okay, like for example, just divide in half, okay, and then you still find the upper sum, right? So right here is your supremum, right there is your supremum, okay, right here is still your supremum, but here is your supremum. For this one, here's your supremum, and there is your supremum. So it means that some part that you get too much, you see, here is like the part that you get too much previously, right now it reduced, you see, it is reduced into this part only, and this part only, that will be calculated as your area, okay. For this one, you see, here is the one that you get too much, okay, but after you do a refine a finer partition, you get only like that part, which is like less than what you have earned before, okay. So we expect that as you do a finer partition, okay, the area of the strip, for example, this one you do 7 1 2 3 4 5 6 7 subinterval, okay, these lower sum and the upper sum for the new partition should be a better approximation of the area between the curve and the x-axis, okay. However, we can interpret it this way only for this kind of curve, okay, only for the curve that it is or above the x-axis under the interval of consideration. Okay, so that's roughly speaking the case. All right. Okay, so because of this kind of refinement, okay, of the partition, or if you do finer partition, then we are going to give you this lemma first before we go to the next theorem. Okay, so let your P be a partition of A and B, okay, which is start from x0, x1, x2, etc. to xn, okay, and your x0 is A, your xn is B, and your Q, okay, it is also a partition of your closed interval from A to B, okay, which is start again from x0. However, between xi and xi, between xi minus 1 and xi, you insert one more point there, okay, one more partition, okay, between these sub interval, okay. We called this one is a refinement, okay, of the partition P. So it's going to be this a partition over the same closed interval, but this Q get more intervals, get more subintervals. Okay, so if this is the case, then you are going to have that your upper sum, okay, over the partition P will be always greater than the upper sum over a partition Q. Okay, so the new refinement will get a smaller value of the upper sum, as we have previously in the example that I just gave it to you, right? And the lower sum of the P will be less than or equals to the lower sum of the refinement. Okay, this one also like what we have seen in the example as I showed you in the picture previously. Okay, so let us prove this lemma first. All right, and the lemma actually it depends on the property of the supremum and the infimum. Okay, so for example, if you look at this interval, the subinterval from xi minus 1 to xi, okay, only the one that you divide into one more point, okay, and if you look at the supremum of this one, okay, over the smaller interval and the supremum of this one over another part of the interval, okay, so which one will be greater? Because this one is the supremum over a bigger interval, okay, it may be, okay, it may be contain some value that is greater than the smaller interval, right? So it means that for this one, if you need to compare, the supremum of the larger interval will be greater than or equals to. So on the same token, this one will be also greater than or equals to the supremum of the other half. I mean, the we are not so sure whether it's half or not, but it just on the other side, okay, on the right hand side of your new point of division here, okay. And what we have for the upper sum is that if you're talking about the upper sum of this new partition Q, okay, is going to be somewhat the same, okay, up to like before this point, right, before the xi minus 1, it will be mj delta, let's call the, actually it is like what, xj minus xj minus 1, is it? So this one is the length of each interval, which sometimes we call it like delta xj. Okay, and then this m, okay, with the length of this subinterval, the new subinterval between xi minus 1 and, you see for this one, xi minus 1 and x star, and another one let's call the m tilde before xi, I mean together with xi minus xi star, which is this next interval here. Okay, and then you just add the rest, which is from I plus 1 to the last one, your n. Okay, and the same supremum and xj minus xj minus 1 to the last one. Okay, so what is this m? This m is the supremum of your f of x over the closed interval from xi minus 1 to x star, and your m tilde, it is also the supremum, okay, over the closed interval from x star to xi. Okay, however, as we have it, I mean as we have this property over here, this one actually is your capital M, this one is actually your capital M tilde. Okay, so both of them, for example this one is less than or equals to, let's say this one is M sub I, okay, because it is the supremum of the function value inside this interval from I minus 1 to xi. Okay, so this one will be less than or equals to mi, this one also will be less than or equals to mi. So as the inequality, okay, you can combine this one, so here from 1 to I minus 1 mj, xj and xj minus 1, this one you can combine as the mi, okay, and then x star xi minus 1 and xi minus x star, okay, and add the rest, right, mj xj minus xj minus 1. Okay, however this one your x star will cancel and you end up with xi minus xi minus 1 multiplied with mi. So it means that you can add all these three terms together to get back your what, the upper sum of your I'm sorry, this one should be the partition goes first and then the f, right? Okay, the partition go first and then the f. This one as well, the partition p go first and then the function f. Okay, because it is like the partition without the x star. Okay, so this is the idea to get your first inequality. So of course your second inequality, it will depends on this kind of properties of infimum as well. So we are going to let you do it by yourself at home. Okay. So I mean, as you have a bigger, I'm sorry, what should I say, a finer partition, okay, you are going to have this kind of inequality always. Okay. So let us right now we are ready to establish the 7.1.2, okay, which is saying that if your f is a bounded function over this interval from a to b, then your lower integral and the upper integral always exist, and the lower integral will be always less than or equals to the upper integral, which is, I mean, that makes sense, right? That really makes sense. Okay, so let us do the proof. Okay, so we are going to let your P and your Q be any partition of the closed interval from A to B. Okay, then all what you know is that the lower sum, okay, will be less than or equals to the lower sum of P union Q, right? Because this one is the refinement, one of the refinement of P, right? So this inequality came from that previous lemma, okay? And then by the definition of the lower sum and the upper sum, because this one depends on, I mean the lower sum depends on the infimum of the function over each interval, but the upper sum depends on the supremum, okay, of a function in each interval. So this one directly from the definition, okay, of the lower sum and the upper sum, okay, we got this kind of inequality immediately. And then again from the refinement, okay, from the previous lemma, okay, this upper sum will be less than or equals to the upper sum of only Q. Let me use the Q. Okay, so this time we use the Q. So this one is from the lemma. Okay, all right. So what does this mean? What does this mean? It means that your lower sum for this partition P, okay, got a bound here. Okay, this one is the upper bound of your lower sum, right? So this UQF is the upper bound of this set, the LPF, okay, as your P is a partition of this closed interval from A to B. Okay, so it means that your lower integral LF, which is the supremum of all lower sum, okay, over any partition of AB, okay, it will be of course less than or equals to this upper bound, right? Because the supremum will be less than or equals to the upper bound for any partition Q of this closed interval AB. Okay. Okay. So what does this mean? It means that of course the lower sum, the lower integral exists, right? Right. However, immediately it is follows that, okay, as a consequence, this one that exists, okay, is immediately a lower bound, one of the lower bound of the what? Of this set, right? Or the upper sum, okay, for each and every Q that is a partition of the closed interval AB as well. Okay, so what does this mean? So it means that the lower bound will be less than or equals to this infimum, right, of all upper sum over a partition, I mean over any partition given, all right, but this infimum, it is the upper integral. Okay, So we got the inequality that we need, that your lower integral will be less than or equals to the upper integral, okay, and both of them, I mean, exist. All right. So what should we say? Okay, what should we say for the integration itself? Okay, so we are going to say that if your f is a function from closed interval a b to r, and again it is still bounded, your f is said to be integrable or Riemann integrable if your lower sum and the upper sum are the same. Okay, so that if a difference of your lower sum and the upper sum are zero, okay, then this will be the definition of a Riemann integrable of a function over that closed interval. And of course this value, I mean, you can choose either a lower or the upper sum. This one is called a Riemann integral of f over that closed interval from a to b, and it is denoted by the one that you familiar with, which is the integration from a to b of f of x dx, or simply sometimes by this one. And moreover, okay, there's integration from b to a, it is defined to be the negative of the integration from a to b of the function f. Okay, so if you switch the order of integration, you just insert the negative in front of it. And of course, if you find the integration from a to a of a function f, it will equals to 0. Okay, so let us try to see whether this function on this example is integrable or not. Okay, so can you see that this function is bounded? All right, it is bounded above by 1, right, and below by 0. Okay, so if we want to see whether it is integrable or not, okay, let us give you a partition. Okay, so we let this P be any partition of this closed interval from 1 to 2. Okay, and on each subinterval, so let us talk about the subinterval from xi minus 1 to xi. What happened? What is your mi? Your small mi will be the infimum of your function f over this subinterval, right? However, your function f, okay, the function value of f can take only two value, right? Either 1 or 0, depends on whether that particular input is the rational or irrational inside that closed interval, right? Okay, so the infimum, of course, it will equals to 0. On the other hand, if you're talking about the supremum, okay, over the same closed interval, you immediately see that the supremum will be 1. Okay, so this time you can find the lower sum, right? So your lower sum will be summation from I to n, a small mi, and then xi minus 1. However, each and every mi, they are all 0, so this one it is 0. The upper sum for this one will be from 1 to n of a capital Mi xi minus 1. Okay, however, this one always 1, so here you can just stretch it, okay, to be x1 and x0, x2 and x1, x3 and x2, etc. up to xn minus 1, sorry, xn and xn minus 1. Okay, and you should be able to see that it will cancel as a the same as a telescoping cancellation. The first will cancel the last of the next term, the first will cancel the last of the next term, so this one will cancel somewhere here, and this one here will cancel the last one there. So you are going to end up with your xn minus x0, but your xn and x0, it is like 2 and 1, is it, the or the endpoint of the left end and the right end. Okay, so it is 1, and this one, I mean, it is like this for any partition. So what does this mean? It means that the lower integral, which is the which is the supremum of each and every lower sum, right, for any partition however, for each and any partition, this one always 0, so the supremum will be 0. The upper integration, okay, on the other hand, it is the infimum of this one. Again, your P is just a partition, however each and every one of them equals to 1. Okay, so this one is the is the infimum over the set of a constant, so it is 1. So they are not the same. So what does this mean? This f is not Riemann intractable. All right.